So look, we're at 2 minutes past. I think that's probably as good a time as any. So I'll start talking as people start trickling in. They can miss my intro spiel and they'll probably join just in time for Sebastien to start. So thanks for everyone for coming along today, and a big thanks to Dr. Sebastien Lamontagne from CSIRO Land and Water in Adelaide for beaming into your computer screens today to give us our real seminar. So I always like looking into people's background to give the little intro that I'm about to give now. And so to do that one for Sebastien, so looking up his bio on the CSIRO website. So Sebastien has a Bachelor of Science from McGill University, which is a very well-regarded university, a Master's from Alberta, and a PhD from Waterloo. So those of you that are in the groundwater world will probably recognise Waterloo, where there's a really strong groundwater modelling group there. So some very prestigious organisations. So sorry to say this, Sebastien, but I looked it up. You've got almost 30 years of research experience now. And so from my guess, and you can correct me if I'm wrong, but it looks like around 20 of those years have been in Australia. Looking up, one of your first papers that mentions Australia was Blue Lake, from my sort of neck of the woods in South Australia in 2002. So as you'll see, Sebastien's got a really strong background in groundwater, groundwater surface water interactions, and then the use of radioisotopes. So he's done a whole bunch of work in the NT, including some of the stuff that he's going to talk about today. So just a couple of tiny housekeeping things before we hand over to Sebastien. So what we're going to do for the Q&A, if you can find the chat box down the bottom of your screen, if you have a question as the seminar's going, you can type those out and I'll go through those list of questions when we get to the end. But I just want to flag that as a government employee, Sebastien's job is to do the science, not necessarily to provide comment on policy. So if you just keep that in mind when you're typing out your questions, but I'll curate any really out there ones for you, Sebastien. But anyway, that's enough from me. So if we hand over to Sebastien, so thanks for joining us, Sebastien.
Thank you very much, Dylan. I hope everybody can hear me okay. So it's my pleasure to present this work on behalf of my co-authors, which include colleagues from CSIRO, Axel, Christophe, Alec, and Cornelia. Some of your own people from Charles Darwin University, Clément and Diony, as well as the golden treasure of hydrogeology in Australia, Steve Tickle from the NT Department of Environmental Parks and Water Security. What I'm presenting today is overall a fairly small component of a much larger program, geological and bioregional assessment, which aim to look at the potential environmental impact that could be associated with unconventional gas extraction for 3 large sedimentary basins in northern Australia, which include Beetaloo Subbasin. And we'll see how this links to the springs in a few seconds. I would like to do 3 things today, actually. First, I would like to, in case you're not familiar with it, I would like to tell you a little bit more about the Northern Territory's its own wonder to the hydrogeological work, the Cambrian limestone aquifer, a really fascinating system. We'll then show you some of the findings, some of the highlights of the work we've done at the Mataranka Springs. And then we'll link this to another topic, an important one in the context of the development of unconventional gas resources, the one of the vertical hydraulic connectivity in hydrogeological systems. Now, it's important for me to say that this work would not have been possible without the help of many people in the Northern Territory, in particular the stakeholders and the communities around Mataranka. They've really welcomed us to their country. I'm very thankful for this. And that included the rangers from Elsey National Park, where the springs are located, or most of the springs are located, as well as the local communities, the Yangman and the Manggarai, and the Manggarai, the intrepid Manggarai Rangers, who did some of the monitoring we did at the springs. And I'll show you a little bit of that later in the presentation. So I'm a little bit overdue for a return trip to Mataranka because of the pandemic, but hopefully I will be back soon. Now, I'm come from, as Dylan hinted, I'm all the way from Montreal in Canada, and sometimes people ask me, well, why did you come all the way here to do hydrogeology? You have plenty of groundwater where you come from, and yes, but really one of the reasons why people like me are here to do hydrogeology is this. This is a map of the large sedimentary basins that you have in Australia. And many of these host very large regional to continental scale groundwater systems. Now you often hear that Australia is water limited, the driest inhabited continent and so on. Well, it's true, but one thing that Australia has going for it is these very large groundwater systems. They store large amounts of water and they carry this water from relatively wet to relatively dry areas. Now, you're familiar with some of them. In light blue, we have the Great Artesian Basin over Queensland, New South Wales, and South Australia. But right in the middle of DNT, we have this blue thing here. That's the Cambrian limestone aquifer. Very large as well, 1.5 times the size of Italy. And like all of these regional groundwater flow system, it's not a simple entry and exit point for groundwater. They're very complex with numerous flow paths, and we're still learning about them. And it's some of the things we're learning about them are still very basic. For example, for the Cambrian limestone aquifer, we're still not sure exactly how big it is. The edges are still a little bit fuzzy. Now, the part of the Cambrian limestone aquifer we're especially interested in is the one around in the vicinity of Catherine, a few hundred kilometers south from Darwin. And the reason for this is these two structures here in dark green. They are the two basins of Beetaloo sub-basin. Very deep sedimentary basin hosting prospective shale gas resources. Now, the significance of this is, you can imagine in this case, the Cambrian limestone aquifer, if we look at the Beetaloo sub-basin as some sort of layered cake, the Cambrian limestone aquifer will be right at the top, whereas these deeper geological formation hosting the unconventional gas resource will be kilometers down. So very deep system with the aquifer flowing on top. Now, to enable the extraction of unconventional gas resources, typically requires, in shales at least, requires hydraulic fracturing. And for hydraulic fracturing, you need a source of water. And this water most likely would originate, should the industry develop, from the Cambrian limestone aquifer. So this is the link to the CLA and the link to the springs. As you can see on this slide, we do have a major regional flow path originating from the Georgina basin of the Cambrian limestone aquifer, starting well south in the NT, in the semi-arid region, and it flows over Beetaloo sub-basin and exits at the Mataranka Springs. That's not the only source of water that is thought to contribute to the springs. We have another one originating from a groundwater divide outside of Catherine, flowing from the north and originating in the so-called Daly Basin, from a more, let's call it for today's purpose, the more tropical component of the system. This is a cross-section of the geology in the vicinity of Mataranka. A would be in the south and B north. And it's just to show that as for these large groundwater discharge zones associated with large regional aquifers, they do not happen in a landscape by accident. They're usually associated with some form of structural control. I'll explain briefly what that means. So on this map, you can see different geological formations. On top, we have in light, in some sort of pink color, the Cretaceous sediments, which typically over most of the CLA covers it. However, it turns out in the vicinity of Mataranka, the CLA is exposed to the surface. Now the reason, and then underneath we have other formation, a basalt and a sandstone. Now what probably happened a long time ago, there would have been some geological upheaval that tilted the layers of the cake upward. And as it's more difficult for groundwater to flow through the underlying geological formation, there's a tendency for the groundwater to go up. In addition, you can appreciate from this slide that as we get closer to the spring, the Cambrian limestone aquifer also becomes thinner. That creates another phenomenon, which is the loss of transmissivity. You can stack so much water through a given amount of rock, and if you make that amount of rock smaller, the water has only one way to go, and it's up. And that's what we see here. And the thing to keep in mind is, although the springs at Mataranka, I'm sure many of you are familiar with them, are the most obvious feature, the most obvious expression of this groundwater coming to the surface, it's important to keep in mind that the whole of Elsey National Park and surrounding areas is a groundwater discharge zone through numerous seeps, through transpiration by phareophytes, and so on. There's a few examples of some of the features associated with the discharge zones. Well, of course, we have the springs. We have these spectacular tufa terraces in parts of Elsey National Park. And whilst I said that the limestone is exposed to the surface, it's not quite true. There is on top of them a layer of tufa, which is redeposited limestone that came with the groundwater over very long periods of time. A spectacular environment. The whole landscape at Mataranka has been shaped by being a groundwater discharge zone for a very, very long time. So for the study, we had three questions about the springs. We wanted first to confirm the conceptual model of the springs, which I hinted to with one of the maps earlier on, is that they were fed via two flow paths associated with the Cambrian limestone aquifer. However, there's also the possibility, as the CLA or the tufa is quite exposed, as numerous sinkholes in the vicinity of the park, there could be a component of quick flow of local recharge also contributing to the springs. Also, we were interested to see if there was a deeper contribution from some other geological formation contributing to the springs. And this is something we can only really look at recently, because previous to this, the technology for doing so was not available in Australia. And I'll explain what I mean in a few seconds. Now, the tool that we use for this work was what we call environmental tracers, which is compounds dissolved in groundwater or some properties of the water molecule that can be used to do things like inferring where it came from, how it was added, how the groundwater was recharged to the aquifer, and also to get an idea of how long has the groundwater been traveling before discharging at the springs. This slide shows many of the traces that can be used for putting an age on groundwater. Note the scale at the bottom. The scale is logarithmic, so in a regional groundwater system, it's not unusual to find groundwater anywhere in age from years to decades, centuries, hundreds of thousands of years. In the context of Beetaloo, maybe even older. Now, this also shows one of the problems we always have when we first discuss with our clients what needs to be done. They're always a bit frightened by the number of traces we want to measure. And they always ask us, well, can't you just pick the best one? No, it's not possible. As you can see, the ellipses on the graph shows the window of time over which a given tracer can give you an age for groundwater. So there's no tracer that can give you an age for groundwater over the whole gamut of potential age in a regional context. You have to measure several if you want to get an idea of what's there. And because of the way groundwater flow system evolve and because of the way we sample them, we almost never find a patch of groundwater that has one narrow age distribution. Usually it's a mixture. Now today I'll show you some example of how this works. We'll look at a monitoring program later on using the stable isotopes of water to look at very, very young water. We also have tritium, which is radioactive water, which can be used to look at relatively young groundwater, recharged since the 1950s or so. We have carbon-14 that looks at, well, for today's purpose, we'll say intermediate age groundwater, thousands of years, maybe tens of thousands of years. But you also hear a little bit about helium-4. Now, this one is a little bit different. This one can be used to look at very, very, very old groundwater sources. How does this work? Well, at some point or another, our group in Adelaide has measured all of these traces that I've showed on the previous slide, but at present we specialize in measuring only one family of traces, the noble gases. You may remember them, that's the elements at the right of the periodic table of the elements. They're the bane of the chemists all over the world because, you see, they have no chemistry. So if all the elements were like the noble gas, we wouldn't need chemists, there would be no chemistry. Well, the fact they have no chemistry is very useful as groundwater tracers because unlike other tracers, most other tracers, carbon-14, for example, which are relatively easy to measure, it's the interpretation that is difficult. You need to do a lot of massaging to get the information you want out of them. The noble gases is the other way around. Once you get the result, that's it. What you see is what you get. It's the measurements that are very difficult. So what you see in the background is my colleague Axel Suko and his pride and joy, the first noble gas analyzer for groundwater samples in Australia. Very, very fancy piece of kit. Whilst the noble gases have no chemistry, one thing that's slightly different about them is that they have different freezing temperatures. So essentially this is a series of fancy cold traps that catch and release different noble gases at different points. And I'm being assured that indeed the coldest point in the whole of Australia is somewhere in that machine. One of the cold trap is almost at absolute zero. Now, whilst I said before that the noble gas have no chemistry and they don't change, once the concentration is set in groundwater at the time of recharge, it doesn't change. That's not always true, and it's not true in particular for helium-4. Now, helium-4 behaves a bit differently than the other traces. Tritium, carbon-14, they tend to start high at the beginning of the flow path and then they disappear over time. Helium is the other way around. It starts at very low concentrations and then over time, but very slowly builds up in groundwater. And this slide explains why. What you see there is the decay series for common naturally occurring radioisotopes. And all rocks, all sediments have small amounts of these. And they produce all sorts of goodies for us who like to study groundwater systems, radium, radon, and so on. But what I want you to look at today is anytime you have an arrow going downwards, that's an alpha decay. And each time you have an alpha decay, one of the products is the nucleus for what will become helium-4. So that's what's happening. So helium-4 builds over time as a function of how much naturally occurring radioactive decay there is in the subsurface. What I will show today is mostly results from one sampling campaign that we had in 2019. On the figure on my left, you see an outline for Elsey National Park. Mataranka is right here. So we sampled 4 of the springs around Mataranka. The 2 major ones, Bitter and Rainbow Springs, which you probably have seen if you've been there. And these are fairly substantial, and they contribute to about half the dry season base flow of the Roper River. However, there are numerous other small seeps and springs throughout the region. And we sampled on 2 other smaller springs, Fig Tree, on the margins of the Roper. And the traditional owners showed up the springs we did not know about on Elsey Creek. called Warlock Pond Spring. In addition to this, we sample groundwater from various monitoring wells in the CLA around the park, with one exception. This well here is the only well in the region that is in a geological formation other than the CLA, in the underlying basalt. In addition to our own sampling, we also collected literature information on at least the hydrochemistry and the stable isotope content for groundwater from the CLA associated with this flow path coming from the south, the Georgina, and the one coming from the north, the Daly. So unless you have any questions, I can go on with the results. I'm kind of looking hard to see through video, but
there's no questions yet, Sebastien.
Okay, good. So what I will do next is not inundate you with everything we've done, but give you an example of what can be done with environmental tracers. Give you an example of how we can use tracers to look at the source of water, feeding, say, a spring. Looking at one other example, looking at the age distribution. One example, looking of how tracers can be used to look at the conditions at the time of recharge when water started its travel through the aquifer. And finally, we'll look at how tracers can be used to look at flow through karst. So the first example is the so-called water sourcing example. So what we have here is the isotopic composition of spring and groundwater for both the samples we collected and the regional ones in the open samples. Now, if you're not familiar with what a stable isotope of water is, just keep in mind for today that all elements have different isotopes of different weights. And this is a relative scale that we have here of the heavy to light isotopes of hydrogen and oxygen in the water molecule. So what quickly becomes apparent on the slide is that all of our samples, ground and spring, tend to be grouped into, they are in two groups. So the first group we have tends to be associated with groundwater samples from the daily flow path, the one that comes from the north, feeding the springs. And one of the springs, Rainbow, has an isotopic signature exactly like that. The other group is consistent with groundwater that comes from the one coming from the south, the Georgina, and the other springs have a signature more consistent with that one. So I think it's a very neat example, very clear cut that, yes, indeed, the springs are fed by these two flow paths, but different springs rely on different flow paths. Now, why there is a difference between the two flow paths is a longer story. All I need to say for today is it probably has to do with the very large climatic gradient in the region, going from the tropics to the semi-arid interior. The second example is more about how you can use tracers to look at the age distribution in groundwater. It's a little bit more difficult, so I'll take you through this a bit more slowly. Now we have three different pairs of tracers showed here. We have tritium, which is our tracer for so-called young groundwater, 50 years or less. Carbon-14 for, we'll say, intermediate age groundwater, thousands of years or so. And then we also have helium-4, which can look at very old groundwater. But let's look first at tritium and carbon-14. Well, in general, we did not find a lot of tritium in spring and groundwater at Mataranka, suggesting that most of the groundwater is what we call regional in scale, was started as journeying groundwater from much further away. Not entirely true. One of the springs, Fig Tree, and one of the groundwater wells, next to it, had appreciable amount of tritium. Now, tritium in rainfall nowadays about 2 tritium units, and the half-life of tritium is 12 years. So assuming there will be only one source of water at the spring, that would mean that this water would be from about 1960s and 70s. But that's not quite the case. If that was the case, if you look at carbon-14, its scale goes from 0 to 100, so-called percent more than carbon. Don't worry about the detail. But what's important to keep in mind is if you find tritium in groundwater, that is only one source of water, carbon-14 will be 100. 50 years is nothing for carbon-14, doesn't have the time to decay. So the fact we find some tritium and some loss of carbon-14 shows that what we are seeing here is a mixture of water that is of various age. Now the two lines that you see here are approximation of different mixture of waters of different age. That gives us some idea of what the average age of groundwater could be at different springs. And essentially, by comparing tritium and carbon-14, basically what it says is Fig Tree Spring, on average, the water could be somewhere between 100 to 200 years. But at the other springs, especially Rainbow and Bitter, there will be many thousands of years. How old we cannot say, but one thing for sure, there's little young groundwater there. Now, if we look at the next figure, B, it's a bit different. So we have helium here. And once again, the hash mark here, that's the background detection limit for tritium. So we can call this water tritium free for now. But the vertical line, that's what the background concentration of helium should be if you look at groundwater that's just been recharged in the last decades. As you can see, some of our springs, including again Fig Tree, had helium at background level, but the other springs, in particular the two large ones, Bitter and Rainbow, and many of the groundwater samples surrounding them, had orders of magnitude more helium than background. Now, at this point, it's not possible to say how old this water is, and I'll explain why. But one thing we know for sure is that in addition to those flow paths from the CLA, there is some deeper source contributing to the springs. And that's not unexpected. If you look at a regional system like CLA and Beetaloo Basin, you would expect some old deep groundwater to also contribute to the springs. The next example is how you can use some traces like noble gases to look at the conditions at the time of recharge. And the question there that we're addressing is this: is whether or not there is a geothermal contribution to the spring. So if you've been to Mataranka, you'll see some of the signs in the park called the springs thermal springs. Well, it's not quite correct. It's true, they are warm, but there's no evidence of a geothermal contribution to this. Now, what you have here is on this figure is the concentration of two of the noble gases, neon and xenon. And the blue line represent the concentration that you would expect to see in the samples if at different temperatures. So one thing that a noble gas are quite a bit different from one to the other. Their solubility changes at different temperature, but in different ways between different gases. So by looking at the changes in the ratio of different noble gases, you can infer the temperature at the time groundwater was recharged. Now you can see none of our samples exactly fall on this blue line. That's because of another process, which we call excess air. Often when you recharge an aquifer, it corresponds to a rise in the water table. And when you do that, you tend to capture little air bubbles. You've seen this when you fill your aquarium. The sand at the bottom has a few bubbles, and after a day or two, they disappear. Well, it's something similar happening often in groundwater system, and this process tends to inject a little bit more gas than you would expect in the groundwater. The short story for the springs is that if you look at the makeup of the noble gases, the inferred temperature at the time of recharge would be around 30 degrees. So the short story is that the springs are warm because it's bloody warm in the territory during the wet season, not because there's a geothermal contribution to the spring. It's also used in useful in the context of quantifying how much that deeper groundwater source is contributing to the springs. What this means that's either that deeper source is not that deep, or that it comes from deep, but it's so small that it doesn't really change the overall temperature. Very quickly, in last in terms of result, I'll show you some of the results of the monitoring that Clément and our friends at Mataranka had done for us. And the idea there was to look for the evidence of quick flow at the springs. Now, groundwater typically happens very slowly if you look at traditional flow process to a porous medium. However, in limestone aquifers, and especially old limestone aquifers, like the Cambrian limestone aquifer, you have solution features, you have karst, you have sinkholes, and then all bets are off. Things can happen a lot quicker when these are present in the landscape. Now, in the previous analysis of the age distribution in the spring, our so-called young tracer was tritium. But tritium can only start to detect groundwater that is at least 2, 3, 5 years old. Whereas at the scale of the springs and Nelson National Park, quick flow would tend to introduce water at the scale of weeks to months. So basically it's invisible to tritium. So the way we address this is by using another gift from Mother Nature, the fact that rainfall from rain event to another tends to vary quite significantly in its isotopic signature. And by chance, it can introduce a natural tracer experiment in our system. So we had a monitoring program for rain and for springs at Mataranka for 2 years. And indeed, the short story there, although there's more to it than that, maybe Clément can tell us the full story in the near future. But we did find evidence for quick flow at least one of the springs, Fig Tree again, the same one where we saw tritium above background, so consistent with that. But no evidence of quick flow at the two major springs, Rainbow and Bitter. So the conclusion of the springs work was, in terms of the role of the Cambrian limestone aquifer, consistent with what had been observed before, the springs are fed by two flow paths, one from the north and one from the south. We also show that there is some local contribution for at least some of the springs. Perhaps the newest finding would be the one about the presence of a older groundwater source. And again, as I said earlier, it's something that we can only address now with the availability of new tracer techniques. Now, unfortunately, whilst we know that there is a contribution from one or more deeper sources to the spring, there's essentially no or very little infrastructure, very few monitoring wells in any of the geological formations elsewhere below the Cambrian limestone aquifer. So we don't know the signature for helium and other tracers in these deeper sources, so we cannot quantify the contribution at the springs at the moment. However, they do demonstrate that there is some underlying vertical connectivity in the system. There is some exchange of groundwater between some deep and some shallower formation. And that's very useful to know. In some other contexts, like some regions elsewhere in Australia that were currently exploited for coal seam gas, this was only found out after exploitation has started, and that created some difficulties. It makes it very difficult to understand if the vertical connectivity is there because it's there naturally or because it was induced by something about the industry. At least we know in the context of the CLA that there is some vertical connectivity now. Now, again, this was only a very small cog in a very big undertaking, the geological and bioregional assessment. Now, even if you're not particularly interested in the topic, I would suggest you may want to have a look at the way this project was delivered. You see, we made a brave new jump to web-based project delivery. The reason for this is, well, last time we did something like this in a coal seam gas context, the end product was a pile of reports 1.5 meters high, and I defy any of you to go through this and keep your marbles together. It becomes untractable, and it's a common problem for environmental impact assessments for large projects throughout Australia. They typically consist of 10,000 pages or more. It's almost unmanageable. So in GBA, what we did instead is to provide all of the information through a web-based tool, a so-called causal network. And instead of reading through pages of a report, you go fishing for the topic through this network that you're interested in. All of the information that you would find in a traditional report will be there by clicking to the right links. And it takes you logically from something like hydraulic fracking to impact on some bird or some fish that is of interest. Now, if you want to look into this, all you need to do is to type GBA Explorer in your favorite web browser and click on the Beetaloo link, and you'll see the spaghetti diagram, and you can start looking at what we've done. Now, in general, looking at the bits of the spaghetti diagram that concern the spring, in our work, there was nothing that was found associated with the development of an unconventional gas industry in Beetaloo that would bring some red flags in terms of danger to the ecosystem. In general, it was of low concern, providing that we using industry best practice and that the appropriate management strategies would be used for things like chemical spills, for example. So that's encouraging. On the other end, it's not only at the springs. We found other evidence elsewhere in the CLA using helium in particular that we tend to find anomalies. We tend to find little hotspots here and there where groundwater in the CLA has more helium, and they tend to be associated with particular type of faults. So there is, again, more evidence that there is some underlying vertical connectivity in the system. And of course, that links it to the topic of how processes like hydraulic fracturing could increase that natural variability. Now, whilst we did the best we could through GBA to quantify this, at the end of the day, a lot of the information used was taken from other studies or from the limited information available for the system. So do we still need to worry about vertical hydraulic conductivity in the system? Is it something we should consider? Now, I will stick my neck out a little bit for the next two slides and try to explain how it works and why it's not simple. The first one is to explain that this movement of solutes and groundwater across geological formation is typically not a straight path. What you have here is a cross-section for Beetaloo subbasin. Now notice that unlike the previous cross-section I've shown around the Mataranka Springs, this one, the scale is in kilometers. We're really dealing with a very substantial geological structure. Now, by comparison, the CLA, which is several hundred meters thick, is not insignificant. At that scale, looks puny. It's this little layer near the top. Now, to illustrate how vertical hydraulic conductivity works, let's imagine you this dot here, this orange dot, in the middle of one potential aquifer very deep in the system, the Bessie Creek sandstone. Let's say that you've just been created, you are a brand new atom of helium-4, and your dream is to come up to the surface somehow. How will you do this? Well, one way you could do this is to travel with groundwater flow and the Bessie sandstone. That's one possibility. The other way would be to slowly diffuse through aquitides geological formation that don't let water flow through easily, but solutes can diffuse through them, providing there's a concentration gradient, but that happens very, very, very slowly, but it's possible. And we've measured this for aquithards using helium in the context of coal seam gas. So that's another mode of transport. But let's say for now that we're traveling happily in the Bessie Creek sandstone. Oh, at some point we could encounter a fault. So we could go up or down in the system, link to another aquifer, travel for a while another aquifer, diffuse to an aquitar, joint where they connect to another aquifer, and so on. So this process of taking things from produced deep down to the surface is not straightforward. It can be quite complicated. The other issue associated with this is the time scale over which this happens. So here again, we're looking at a conceptual scale of transport in the whole of Beetaloo Subbasin. We know that some of the processes associated with the possible conventional gas industry would only happen at a fairly small scale. So if it happens, the industry would only last a few decades. So there would be a need to pump from the CLA from a few decades. Now the regional scale, that's a fairly small disturbance, and that's one of the reasons why it's felt it's unlikely pumping from the CLA hundreds of kilometers away from the spring would create a significant impact. And typically the scale of flow in the CLA itself, we know this reasonably well. It's at the scale of years to centuries to perhaps millennia. We have some ideas at the speed at which groundwater and solutes travel in other parts of the system. It's typically much longer. But again, in the context of Beetaloo, we don't know for sure. And in particular, a recurring problem in this kind of setting is what's the role of faults. Most faults do very little or nothing. Some sometimes contribute a lot to vertical groundwater flow. What does it mean in the context of Beetaloo? I don't know. So I'll conclude by perhaps starting a discussion. So do we need to invest more time and effort to characterize this vertical hydraulic connectivity in the system? That's not up for me to decide. That's up to the stakeholders and discussion that they have with the industry. I suspect, however, that if the committee wants more certainty that it's safe to proceed, we will do a little bit more on that topic. Now, I say this with a little bit of misgiving because to make a substantial improvement in the certainty that we can proceed safely is not going to be a trivial exercise. The deeper you go in groundwater system, the more difficult, the more expensive it gets to do the work. And also, it has to be done in the context of the number of other issues happening in the region. There are other proposals for development associated with the Cambrian limestone aquifer. So I do not have an answer for you today, but I hope that this can be the start of a conversation on the topic. That's it for me. Thank you for your attention, and I am happy to take questions.
All right, so thanks for that, Sebastien. So with everyone on mute, I'll give you here's my microphone over here. Thank you. That was excellent. That was really, really good. I really enjoyed that. So just a note for you sitting behind your computers, everybody. So if you've got any questions for Sebastien, if you start typing them in, I've got two. And then the other thing that I'll do, Sebastien, is when we've finished at the end, I'll put a link to the paper that this is based on because it's freely accessible. So for those of you out there who want to read a little bit further, you should be able to get the paper from the link. Yeah, if not, maybe send me an email. So I'm just going to quickly, I'm copying and pasting these into a Word document. Just so I don't lose them as things go. But so, Peter, we will get to your question, but I'm going to start with an easy one for Sebastien. So there's a question from Annette, which is, why does old groundwater equate to deep groundwater source?
It doesn't have to. So, for example, in the Georgina flow path of the CLA, you would have some groundwater that would be thousands of years or more in age, because the recharge rates are lower under some arid conditions, so the travel time is slower. But the CLA is also what we call an unconfined aquifer. And typically flow processes in unconfined aquifers are relatively quick, whereas the aquifers below tend to be confined aquifer, and their water tends to move more slowly. So for example, the Great Artesian Basin is a confined aquifer, and you can find groundwater there that, so as far as we can tell, could be up to 1 million years old. It just moves very slowly. And I suspect, the suspicion is that in Beetaloo, because of the great depth at which these aquifers are, and at depth, you can imagine they get squished. There's not a lot of pore space for the water to move through anymore. The flow rates are probably very, very slow. But again, at this point is speculation. We have not measured any of this.
All right, thank you, Peter. Sorry, thank you, Sebastien. So here you go. So this is an interesting one, and I guess I'll add to the complexity of it with your comment on faults. But so there's a question here about how long do you feel it would take to develop a high confidence hydrogeological model of the CLA that includes the Mataranka Springs and other groundwater surface water interactions for the area?
That's a very good question indeed. If you talk to any hydrogeological modeler, including faults in their models, is something that they're struggling with to some extent right now. They try very hard. It's not easy. And again, not all faults necessarily have a big impact on flow processes. Some do, some do. So perhaps what we're lacking often is information about those faults. Just finding out where they are is not good enough. You have to be able to characterize their hydraulic properties, and that can be difficult, especially when they're deeper. Another big area of uncertainty at the regional scale is the overall need for not only the springs, but all of the other groundwater dependent ecosystems, in particular the phreatophytes. So there's a huge phreatophyte community associated with the springs, and we're just starting now to look a bit more specifically for their environmental water requirements. So we are some ways, I think, before we can include all of these things in a groundwater model. I'm aware the modelers are trying very hard to incorporate these processes in their model, but it's difficult.
No, as a recovering groundwater modeler, that's very well done, Sebastien. It is challenging. So we've got another one here. So this is from Jenny Davis here at CDU. And so I'll try and paraphrase this. I've got both types of your question, Jenny. So one of the world's closest to Fig Tree Spring has the most diverse assemblage of stygofauna that were found on a campaign there. And so the point here is that could suggest that there is newer water in that bore. So is there more that can be done age-wise to characterize what's going on here?
Yes. Now I think the area around, so Fig Tree Spring is well to the east in the park, and that area, this is where the CLA is especially thin, and where most of the aquifer is actually the tufa. The tufa has lots and lots and lots of cavities and caverns, and if you look at the drill logs in the vicinity of Fig Tree, there's huge sections of the drill logs where they didn't recover anything. So there must be massive caves and underground structures like this underneath the park, and I suspect they're very nice habitat for stygofauna. And I suspect too, because there's more local recharge in that area, it probably brings more food for them, terrestrial debris and so on. So, and oxygen. So much of the groundwater in the CLA doesn't have much oxygen. So they might be restricted to where they can live, to those areas where they can get some replenishment of oxygen. So my guess at this point, Jenny, is that they like this part of the park because there's lots of big cavities.
Okay, thank you. All right, so we've got a question here from Lachlan Hallett, and I guess now's your last chance if anyone else has got any burning questions. But so the question from Lachlan, and this was about your stable isotope graphs, and this is sort of a point of clarification. So is the point here that most of the springs, most springs have a dominantly Georgina-like source, and Rainbow Spring had a predominantly daily source? Is that right?
Yes, that's correct.
Well, there we go. There's an easy one. So I'll just give you 30 seconds, anyone. Does anyone else have any other burning questions? Oh, you got a thanks from Lachlan there.
I don't know if it's burning, but question for Sebastien. Thanks for the talk. It was really amazing. So talking about addressing the hydraulic, the vertical connectivity, would you see any other tracer apart from Helium-4 that could be used to address this question? Or is it really the silver bullet?
Yes, of course. So some of the other tracers that can be used for looking at vertical processes. Well, first, if you have the right setup, you can use hydraulic gradients. You can use salinity. Typically, deeper groundwater tends to be more salty than shallow groundwater. In addition to Helium-4, we're also developing a whole family of we have developed expertise to measure several very exotic and rare isotopes of noble gases or radioisotopes of the noble gas family that can be used to put an age on very, very old groundwaters, hundreds of thousands of years or older. And the challenge for doing this are quite something. So one of these tracers, Krypton 81, its abundance is it's like 1 grain of rice in the annual world production of rice in a year. So measuring some of these traces is difficult, but we are gradually developing the expertise for looking at these older groundwaters. It's not only for this context, but of course some of my colleagues here are also involved in the design of nuclear waste repositories, for example. And there again, you want to put them deep, you want to put them in environments where groundwater doesn't move too much. So here again, we try to look at ways to measure this very, very old groundwater. So the problem, we have the tools right now. The problem is that we don't have at Beetaloo, we don't have the infrastructure. There are essentially no monitoring wells of any kind below the sea level. There are a few, not that many. But at the same token, I have to make it very clear here, even if we wanted to do this tomorrow, it would not be simple. It's incredibly costly to put deep wells and to sample them, but it can be done.
So if I just jump in and follow on from that one, Sebastien, so have you seen anything to do with geothermometry, where you basically take basic water chemistry, and then you can relate the chemistry that you see with the temperature at which that water originated from? Do you see any potential at getting an idea of depth, source depth for some of these springs?
Yes, look, I did not show this, but hydrochemistry is one of the families of tracers we looked at. And yes, there's no reason why you couldn't do this as well. It's something that's routinely done in the context of coal seam gas. The problem we have with hydrochemistry, specifically at Mataranka, is that a lot of it involves carbonate chemistry. And as you can imagine, groundwater rich in carbonates discharging to the surface, there's an awful lot of complicated chemistry that goes on near the surface. So the interpretation of the major ions in the system is complicated by extensive groundwater surface water interaction near the surface. But yes, you could easily imagine that hydrochemistry could be one way to investigate the scale at which groundwater flows in the deeper aquifers in particular.
All right, so I think what we will do is we'll draw a line under that one there. So just again, well, I'll do the clap again. But thanks a lot for that, Sebastien. That was really excellent. So thanks a lot for coming out and giving us a presentation today. And yeah, we will see you in May, hopefully.
Thank you. I'm looking forward to be back in the Northern Territory.
All right, thanks a lot. And thanks for joining us, everybody.